Okay. Okay, so welcome everybody. We start today's section of our teaching week. I'm glad to introduce you Damir Kralj from Boškovic Institute, Croatia. He's an expert in crystallization, biomineralization. So it is following the path of this week that when the crystallization, the biomineralization process was one of the main topics of this year. And we actually differentiated the teaching topic among the 3 years. So let's say the first year more basic things, the second year more fishery, and the third one is more general on economics and socioeconomics aspect. So this week, as I said, we had a number of lectures on geochemistry, biomineralization, chemistry, and we had Frederick Moran and Jeb Kendorp, and now we have Damir, and this afternoon we are going to close this topic with the lecture of Jonathan Harris. So let's start the day. Enjoy your lecture, Damir, and now the stage is yours. Thanks.
Okay. Thank you. Can you see the screen?
No, it's not share now. You need to restore.
It's not share. Okay. Is it okay now?
No, you should redo the same things as before. Okay. Now we see your screen.
Okay. Is it okay now?
Yes.
Yes.
Okay. Thank you. Sorry.
Welcome.
First, I will try to introduce myself. My name is Damir Kralj. I am physical chemist. I am from Boškovic Institute, Zagreb, from Croatia. In the next few lectures, I will try to give you information about crystallization and biomineralization in the environment, and I will try to tell you something about kinetics and mechanism of precipitation, crystallization processes, and also very basic information about calcium carbonate. I'm sure that you know much about that. And finally, I'll give you 2 lectures with the examples on investigation of calcium carbonate as a model system in biomineralization, but also in the environment. I will start now with kinetics and mechanism of precipitation, crystallization process. You see two terms, precipitation and crystallization. I will explain later on why. So first definition about precipitation. Precipitation is physical-chemical process of formation of new phase in homogeneous system. According to this definition, precipitation is formation of liquid in gas. So rain droplets are actually precipitate appearing in the clouds. Another example is formation of carbon dioxide bubbles in a carbonated solution. So this is example of formation of gas in liquid phase. Solid in liquid is example of smoke. This is also precipitation. But when we talk about precipitation in limited sense, then we talk about formation of solid in a liquid phase, formation of crystals in a solution or later on in the suspension. I will start with very few examples to discriminate and to explain what is crystallization and what is precipitation. These examples are from chemistry courses from primary school, high school, even from university. So first example of crystallization is copper sulfate pentahydrate, blue vitriol. And this kind of crystallization is performed by entering some seed crystals in a saturated solution or supersaturated solution, and after some time, nice and large crystals appear. What is typical for this system is the solubility of copper sulfate pentahydrate, which is relatively high. It is about 10.5 grams per liter. Crystals that are obtained are large. Another similar example is sodium chloride crystallization that is performed by evaporation from saturated solution. Typical for sodium chloride is that the solubility is even much higher than in the case of copper sulfate, and the large crystals can be easily obtained also in this system. Precipitation, examples of precipitation also from a course from analytical chemistry. Precipitation of silver chloride is a kind of analytical techniques for determination of chloride in water. And such processes introduced and started by pouring one of the solution into another, and typically immediately after mixing the solution, precipitate occur, precipitate in the form of very tiny crystals, colloidal crystals. Solubility of sodium silver chloride is relatively low. We talk about milligrams, 5.2 milligrams at 50 degrees. As I said before, the crystals are very small. They are micron size. Similar example is with silver chromite. This is well-known Moore method where silver chromite is used as indicator. This process starts by mixing diluted silver nitrate solution with potassium chromate. The solubility of this precipitate will appear immediately is also relatively low. It is about 50 milligrams per liter, and the particles are extremely small. They are of micron size. And finally, some examples of crystallization and precipitation in the same system. So well-known example is calcite, precipitation of calcite in the form of iron spar, but also calcite can be, as you will see later on, possible to precipitate in the form of very small crystal, micron or submicron size. Similar example is with gypsum. It is a calcium sulfate dehydrate which can be produced. It was found in some caves in the form of extremely large crystals, but it can also be precipitated in the form of very tiny, small crystals. So from the examples here, we can conclude it what is precipitation of crystallization. If we talk about crystallization, we learn that typically large crystals are produced. Also, slow process, this crystallization is very slow process. Evaporation will last for some time, even days or months. On the other hand, precipitation is a fast process, and crystals that appear are very small. Also, we can correlate large crystals with very soluble salt, typically soluble salt. And small crystals are typically less soluble salts. We can conclude that precipitation can very often be crystalline. We saw under these Microsoft slides. And there are also some empirical rules how to define precipitation. So very often people said precipitation is crystallization of slightly soluble salts. Also, people used to say that precipitation is fast crystallization. So we correlate crystallization with soluble salts and large crystal. Precipitation is slightly soluble salt and small crystal. And generally, my conclusion is that precipitation is more general term, and I will, in a further lectures, use this expression typically. We also introduced some terms before. One of such terms is solubility. Solubility is defined as a maximum amount of substance that could dissolve in a volume of solvent at certain temperature. It's a bit important to say at defined temperature. There are some empirical classification of solubility. So typically insoluble materials, although all materials are soluble, are those with in which the concentration in saturated solution is about 0.01 mole per liter. Slightly soluble salts are those with which the solubility is between 0.01 and 0.1 mole per liter, while soluble salts are those with solubility larger than 0.1 mole. There are also a lot of empirical solubility rules. It's good to know when you come in contact with a new precipitation system. One of these, they said that, for example, all sodium and potassium as well as ammonium salts are soluble. Also, nitrate, acetate, and perchlorates are soluble, similar like chlorides, bromides, and iodides. On the other hand, sulfates, majority of the sulfates are soluble, but there are some exceptions, like calcium sulfate or barium sulfate. Similarly, all silver, lead, and mercury salts are insoluble. And finally, about carbonates, carbonates are typically considered an oxide as an insoluble salt, but there are also some examples. For example, sodium carbonate is soluble salt. We also talk about equilibrium in a heterogeneous system, which can describe the solubility. So I will explain it on the example of slightly soluble salt, which dissociate on the cation and anion. So in any saturated solution in which is in equilibrium with undissolved material, so in any suspension, there is a kind of dynamic equilibrium. Dynamic equilibrium means, it's shown on this example, that amount of the crystals that enter the crystal is equal to amount of crystal ions enter the crystal is identical to amount of ions leaving the crystal. So the solution rate and precipitation or crystallization rate are identical. The value which described equilibrium is solubility product. More probably you met it before. So solubility product is actually defined as a product of ions in a solution at equilibrium. So for a salt like calcium carbonate, which is 1,1 salt, solubility product is defined as a product of calcium and carbonate concentration, actual activity of calcium and carbonate ion. Similar is with silver chloride, but for example of aluminum hydroxide, it dissociate in 1 aluminum ion and 3 hydroxide ions. So solubility product is defined as a product of activity of aluminum times the activity of hydroxide on a certain potential. Similar is for calcium fluoride, for example. One of the possibility that comes out from the solubility product, this is value that you can find in any thermodynamic basis. It is stabilized version. So on the example of magnesium carbonate, it is possible to learn that solubility product is defined like a product of activities or concentrations here. It's equal to concentration of magnesium in a solution, in a saturated solution, in a solution in equilibrium, but it's also identical to concentration or activity of carbonate ion. So solubility is actually equal to the second root of the solubility product. For magnesium fluoride, for example, expression said that solubility is identical of magnesium fluoride is identical to concentration of magnesium ion, but also to one half of the fluoride ion that dissociate from magnesium chloride 2. So the solubility can be estimated and shown at the third root of solubility product. All these expressions are valid for simple system which you introduce salt in a pure water. On the following example, it's demonstrate that solubility calculated from solubility product can be compared only for the system we have identical number of ions in the structure. So magnesium carbonate is a system with one cation and one anion, similar with lead sulfide, barium chromate. So from the solubility product is calculate the solubility, actual solubility of these salts, and they can be directly compared. The solubility of other set of species is calcium hydroxide with species with compounds with 3 ions can be also compared, but only this one can be compared in this simple way. When we talk about solubility, we have to mention the factors, parameters that determine the solubility. The solubility is primarily determined by temperature. Typically, the solubility of ionic compounds increase with increasing the temperature. Here is shown several examples for ionic salts. I just said all these salts are very soluble. One example is, for example, cerium sulfide, which lower the solubility with increasing the temperature. Another parameter that determines the solubility is complexation of constituent ions. So if you, in a solution suspension of calcium carbon, which dissociate to calcium and carbon ions, introduce ethylene diamine tetraacetic complexon, that some part of calcium will be complexed, so the equilibrium will be moved to the right side, and calcium carbonate solubility will be increased. Similarly, is with the addition of strong acid. Strong acid can strongly increase the solubility of salts of weak acid like carbonates, fluoride, phosphides by this equation. And finally, the addition of common ion in a solution can decrease the solubility. So if you introduce in a calcium carbonate solution with dissociate in this way, some additional calcium salt, soluble calcium salt, for example, calcium chloride, the solubility or the equilibrium will be moved on the left side, and the solubility will be of calcium carbonate will be diminished. Solution stability should be somehow measured. We already learned that saturated solution is solution in which solid phase is in equilibrium with the solution, and in this system there are no dissolution or no precipitation. On the other way, in the undersaturated solution, this is solution. On this example is shown for sodium chloride. In this solution, the concentration of ion in the solution is lower than the solubility. In such system, the solid phase, if introduced, will be dissolved. And finally, in the supersaturated solution, precipitation of solid phase can appear. Typically, for the system of slightly soluble salts, supersaturation can be defined in several ways, which are convenient for certain precipitation systems. So, typical thermodynamic definition is a precipitation affinity, defined in this way. This is actually the difference of logarithm of concentration in a solution and equilibrium concentration. Saturation ratio is simply ratio of concentration of solution and equilibrium. Y value, absolute supersaturation is different of solution, concentration is solution and solubility, while relative supersaturation is defined as a difference of absolute supersaturation and solubility. And finally, saturation index. I mention it here because in an environmental system, people like to use this expression as which is actually the logarithm of relative supersaturation of saturation ratio. Another important value, important for performing the precipitation experiments, is a way how to initiate precipitation or crystallization. The easiest way and most common way is by changing the temperature. I already said before that typically temperature increase the solubility of ionic salts. So in the case, for example, of sodium nitrate solubility at about 30 degrees or 40 degrees is about 100 grams per liter. So if you have a saturated solution of sodium nitrate and just suddenly decrease temperature, for example, close to the zero, then the precipitation or in this case, actually, this will be crystallization. Crystallization will start, and finally, the concentration will be about 17 grams. So 30 grams will appear in the solution. Another way of initiating the precipitation is evaporation of solvent. It change in this way the constituent and concentration is changed by limiting the concentration of a solution. And finally, actually there are another ways, but I will mention only three. The chemical reaction is the way of mixing the component, precipitation component, can initiate the precipitation. This is very convenient way of starting the precipitation because this way is very fast. Changing the temperature and evaporation are slow processes, but this is very fast way of attaining the supersaturation. In this system, it may be very important because precipitation also very fast process. So if you try to follow a fast process, then you have very fastly initiate the precipitation. So don't have some overlap of these two processes. On this several example, I will show you how to start precipitation by chemical reaction. For that purpose, one should use soluble salt which contain constituent ion, for example, soluble salt AX plus soluble salt BY. Then you can obtain insoluble salt precipitate AB, and in a solution will remain X and Y, which are soluble. On the example of silver nitrate, precipitation is started by mixing silver nitrate, which is well soluble. Similarly, the potassium chromate is soluble, and silver chromate will precipitate, and in the solution will remain potassium ions and nitrate ions. With calcium chromate, in this case, it is shown that one can mix silver solution, chromate solution in water, or it's not necessary to exist water. You can just mix these two solution and precipitate that very fast. Another way is to apply, for example, precipitation calcium carbonate. You put the carbonate solution in a beaker and then fast or not so fast, introduce calcium solution, and mixing calcium chloride and sodium carbonate will appear calcium carbonate in the form of white precipitate, and sodium and chloride ions will also remain in solution. Few words about the importance of investigation of crystallization or precipitation. This process is extremely important in geology, geochemistry, and also oceanology, because formation of all sedimentary rocks and minerals is started by precipitation or crystallization. And in that case, it's not always necessary to have a precipitation or crystallization in a form of in an aqueous solution. Crystallization can also be started in a melt, and this is something what really happened in the Earth interior. Also, in geochemistry, seawater buffering is very much related to calcium carbonate precipitation, which has also implication on global warming and all these things we are talking now about environmental protection. Precipitation is important in technology. If we consider that probably the first technological process in history was production of alum in old Egypt, and after that all this production evolved, and nowadays about 60 to 70% of products of basic chemical industry and pharmaceutical industry is related somehow to precipitation or crystallization. And it is not, I should also emphasize that when we talk about technological crystallization, technological system, unwanted precipitation is also in the form of incrustation or line scale formation is also very important parameter that can change the efficiency of the systems, and therefore knowledge about this process is necessary. And what is more convenient and what is more close to your expertise is precipitation in biomedicine, biology, and material science. It is relation to biomineralization, so formation of bone, teeth, shells, but also to pathological mineralization in the human and other living tissues. Finally, environmental protection is related, but about these things you can be informed from literature. And now I will switch to precipitation, to mechanisms of precipitation, crystallization process. According to definition we gave before, this is a physical chemical process of formation of a new phase in homogeneous system. Actually, precipitation or crystallization is not a single process. This is a stepwise process which include at least 3 processes which go simultaneously, but there are also some interplay or chain between all these. The first of the process is definitely nucleation. We started in a supersaturated solution, and it proceeds. This is a very energetically demanding process, and this is the first process in which the formation new phase appear. After that, supersaturation started to decrease after the process known as a crystal growth, and finally the aging is process which take place very close to equilibrium system, and this is actually common name for many different processes like solution mediated transformation, solid state transformation, coagulation, sedimentation, sintering, oswald ripening, and so on and so on. I'll give you much more information now about nucleation and the crystal growth. So nucleation is a process of initial formation of new phase in a homogeneous solution. It is an energetically most demanding process, and there are several theories which describe this process, but generally accepted, and the theory which gives answer to last question that arises here is the so-called classical nucleation theory, which defined the critical nucleus or any nucleus as a tiny piece of solid phase which possess all chemical and physical processes of macroscopic structure. This is a claim which can be sometimes problematic, because you can imagine that nuclei that is dimensions of few constituting units don't have really all these macroscopic parameters that I show. On this graph is schematically show the energetics of nucleation process, and this is a resulting curve which show the change of Gibbs energy with the size of critical nucleus. Actually, any new phase which appear in a homogeneous system, crystal phase, solid phase, has two contributions to overall energetic system. This is a surface change of surface. We typically increase the Gibbs energy, and change of volume which decrease. So resulting curve is here, and this curve show the maximum that is called critical. This size correspond, the size of nuclei correspond to critical nuclei. All nuclei or embryo that are that are smaller than this one, spontaneously stabilized by their dissolution or their growth. But when critical nuclei pass this barrier, they can only by growth stabilize the overall system. That's about nucleation. There are also several empirical rules which can discriminate the nucleation mechanism. I didn't mention before that nucleation is a process which is on the scale of practically ions. The nuclei are very small. They are also very unstable, and their formation in a volume is unpredictable. Therefore, it's very difficult to conclude about nucleation by direct observation. Therefore, scientists conclude typically about nucleation from chemical, mineralogical composition, number and size of crystals. So crystallization gave us, crystals give us information about nucleation. So one empirical way of discriminating nucleation mechanism is actually the number of nuclei. Again, we show on this schematic diagram which correlate the initial supersaturation and number of particles. So if you start nucleation at low supersaturation, then relatively low number of particles. Supersaturation means that the solution is supersaturated. Relatively small number of particles will be increased, but the increase will correlate the increase of initial supersaturation. However, at a certain critical value, the number will drastically increase, and this increase is exponential. So this region here is so-called heterogeneous nucleation domain. In this domain, actually, the nucleation formation in new phase is catalyzed by the suspended impurities that are always present in the system. Number of these particles is relatively low, and it's order of 10 to 6 to 10 to 7 per cubic centimeter. In this area, in the area of homogeneous nucleation, nucleation is actually the result of collisions of constituent ions, and number of these particles when past this critical value is extremely high, and it could be 10 to 7 up to 10 to 12 particles per cubic milliliters. Already said that the relations of nucleation rate is actually an exponential relation to supersaturation. Another process that is actually characterized by significant change of concentration in a solution, this is a process which is observable, is crystal growth. Crystal growth can be visualized by continuous incorporation of constituent ions into crystals, which are in contact with supersaturated solution. Incorporation typically appear in an energetically favored position at the crystal surface. Namely, incorporation doesn't appear here on the flat surface. It appears the incorporation happen either on the steps or on the king position. This is king, this is the step. Crystal growth is actually a consecutive process. It means that during the crystal growth, several processes take place. The first of them is a diffusion of constituting units in solution up to the surface. When they enter the surface or close to the surface in the absorption layer, they jump to the surface. Constituting units can move on the surface. They can move also on the steps or the edges, and finally they integrate in a energetically favored position. They integrate it in a crystal plates. The slowest of these processes, which follow each other, is actually the rate determining process. So rate determining process can be diffusion, it can be adsorption, surface nucleation, or spiral dislocation. And all these processes are expressed with some mathematical, shown with some mathematical expression, and the rate is either linear dependent on the supersaturation. They can be also linear dependent in the case of adsorption control process. And finally, if a surface nucleation responsible is the slowest process, then there is exponential relation of the rate on supersaturation, or it can be so-called in a parabolic relation. So the rate is described in this relatively simple way. These two cases, surface control mechanisms, are very often found in a realistic system. So I will try to show and to explain you how it happens. So on this drawing, you can see that this process starts with incorporation units in the crystal structure. If the active plates are not present, then they should be formed. They should be formed by a process of surface nucleation. So the rate here is an example of surface nucleation that is relatively slow and that is relatively fast. And this process is described with these exponential relations. This process of exponential growth mechanism, they typically run at high supersaturation. Growth at spiral dislocation can proceed on low supersaturation. Actually, it was found experimentally that crystal can grow at relatively low supersaturation, and it was surprising because supersaturation, formation of new nuclei demands really high supersaturation, and the explanation for growth at low supersaturation is related to the fact that in real crystals, the steps are always present on the crystal as a kind of surface imperfection. This imperfection is something that is called screw dislocation. So there is no need to continuously form a new nuclei. Therefore, this is something that is practically always present, as you can see in the next example, where the crystal surfaces are visualized during the growth by IFM method. And on this example, you can see grow by surface nucleation. You can see surface nuclei, which is spreading around, forming new forms that are finally, you can see here, intergrow each in this is another system of polynuclear mechanism where nuclei grow and finally give more or less perfect plane. Growth on spiral step is really visual. This is the dislocation, which is constant emerge, constant source of a new phase, and they are growing in a kind of spiral. This spiral has shape-full triangle. But in a real system, these two processes are going on simultaneously. The supersaturation is high, so you can see the spiral growth is emphasized with the surface nucleation. Actually, in this system, the overall growth is a result of the sum of growth on spiral step and growth on surface nucleation. I should also mention the impurities and their role in the crystal growth. Impurities are defined as foreign substances other than precipitating ions that are present in the system. On the other way, additives are also impurities on this definition, but they are deliberately added in the system. Impurities that are present in the system are contact with crystallizing compound, and they typically adsorb on the surfaces. They can, after the adsorption, stay adsorbed at the terraces, but they can move during these processes to the growing step if they are mobile enough. Impurities typically decrease the growth rate because if they adsorb on active sites on the surface, they impede the progress of the reactions. Occasionally, they can increase the growth rate, but in this case, it means that after the incorporation in the structure, they change the crystal properties like interfacial energy or even change the solubility. So as a conclusion, it's possible to say impurities typically change the crystal morphology, and also they can change the growth mechanism. They don't have, but they can. It depends on their properties, on their interactions and the interface. And a legitimate question is why to investigate in crystal growth kinetics and mechanism. Answer is relatively simple. On that way, it's possible to control the physical and chemical properties of precipitate like polymorphism, size distribution, or morphology. Namely, from the precipitation kinetic data, it's possible to conclude the precipitation mechanism, and each precipitation mechanism actually gives crystals of different properties. So here I just mentioned data, which are the critical precipitation parameters that could be controlled in order to control the structure, chemical size, and other crystal properties that are initial concentration of reactant concentration ratio, temperature, of course, hydrodynamics. This is the way how we mix the solution. And finally, the addition or additive addition. I will also give you now some practical idea about the possible research strategy of precipitation process. So first step when you meet a new precipitation system is to make some screening experiments. One of this way of producing is a construction of precipitation or phase diagram. Phase diagram, this is what you can hear here. You can see here it's very schematically shown. It's a graphical presentation of precipitation system of slightly soluble salts which dissociate in a way you can see here. So In such screening, you change the concentration of reactant, so you change two solutions and see what happened, what appear, what kind of properties you can emphasize. So if you do it on the systematic way, then you increase the concentration of one component or concentration of another component. You notice here the concentration grow, increase of concentration is in this direction. So on this diagram, you can see some lines. These lines are called isorbons. They are lines of constant relative supersaturation. The first line you can obtain here, it is in a low concentration region, is so-called solubility boundary. The relative supersaturation here is 0. So in this region, at low concentration, there is no precipitation. So precipitation can proceed in this region by increasing the concentration of the reactant. In a real system, no precipitation will be also observed here. This is called metastable solution, metastable region, and this line is called metastability limit or precipitation boundary. So within this region, solution is really very slowly, very low supersaturation. Higher supersaturation is given by obtained by increasing the concentration, and in this region, with the increase, you can observe different kind of crystals. For example, compound crystal can be found at the low supersaturation region. So this is a region where we have a heterogeneous nucleation, or medium supersaturation is here, but high supersaturation region is a region in which homogeneous nucleation is obtained. In this region, the size of crystallines is typically very low. That was the example of silver chloride, silver carbonate, calcium carbonate precipitation, which is initial, this process is initial with introduction of a very high concentration of reactants. Another strategy is actually of strategy of investigation of precipitation is investigation of precipitation kinetics and mechanism. On this picture here, you can see experimental setup of this kind of measurements, and it is made of a suitable beaker, which should provide control of temperature. It is provided by double jacket introduction of hot or cold water. Also in this system, you have to provide stirring. The precipitation is actually started by pouring. I see example of calcium carbonate precipitation. I mix some calcium solution and carbonate solution. And finally, you have to follow what is called kinetics of the process by some suitable measurement units, some suitable sensor. For example, in the case of calcium carbonate, it may be pH electrode, so you can change the follow the change of pH. You can also change the follow the change of activity of compounds. You can also follow the conductivity, or you can periodically sample the solution and determine the chemical composition of this. So from this initial starting the menu, this is called data acquisition. You get a pair of values, time versus pH, and this is graphical presentation of this data. You can see that pH in this system decreased. It changed from the starting value to the value. This is apparently in a kind of equilibrium. From this curve, you can conclude there is kind of equilibrium obtained after 20 or 25 minutes. In another step of this process, you have analysis of grow kinetic data. From this pH there, you can calculate the concentration of the reactant by some processes, or if you use selective electrode, then you can obtain directly the concentration of a certain ion. You can actually obtain the activity that should be later on calculated the total concentration. Here on this slide, you can see several curves, several progress curve. So it means that this process can go, they show that process can go relatively fast to the one equilibrium, or the equilibrium value can be a bit different. After progress curve, next step is actually calculation of growth rate and supersaturation. Growth rate is actually defined as a difference between the concentration at certain period of time, and actually this concentration is directly correlated with the change of the mass or any other volume or something like that of precipitate. The supersaturation is a calculated value somehow, and you can see here that in this system, rate is a kind of curve which shows supersaturation actually started here at low supersaturation. So supersaturation go down and finally finish at supersaturation 0. There is no growth. From these curves, in the final step, that is actually the testing of theoretical crystal growth law models. We mentioned that is in this step, we correlate actually the growth rate with respective model, and the straight line actually indicate that the mechanism is exactly what we assume, what we tested. So in this case, we have a rate that is proportional to rate constant and supersaturation on the second power of 2. And this is actually the end of the process of analysis. From this point, we can conclude that this is second order, and in this case, this is another case not related with this. We find some exponential relation of growth rate with supersaturation. Analytical characterization of solution in solid phase is also part of the activity, and it's typically proceed during the process. Solution should be characterized, of course, to have information of the concentration of reactant, but solid state phase should be and could be analyzed by using technique like those responsible for chemical structure analysis, like X-ray diffraction, EPR, NMR, or infrared spectroscopy. Morphology is typically of the precipitate analyzed by some kind of microscopy, electron microscopy, or light microscopy, crystal size distribution by device, or it can even be observed under the microscope. Chemical analysis of solution, but also precipitate, modern techniques are chromatography, spectroscopy, and so on and so on. And that's all about this part. If you don't mind, we can have, it will take me 5 minutes to prepare another lecture, so we can go on after that. Is it okay?
Yes, it's okay. Thank you.
Okay.
See you in minutes.
So I can start if you don't mind. Can you see the presentation? Can we start now?
Okay, Professor, you need to share the screen again.
Okay.
Yes.
Okay, I'll start now.
Yeah.
Okay.
Oops. Damir,
Hey.
another 2 minutes ago.
Okay.
Okay, grazie.
Wait
Thank you.
just for.
No, it's fine. It's fine.
Thank you. Okay, Professor, we can continue. We can see your screen now.
Okay,
Yes.
just tell me when I can start. Is it okay now?
Yes.
Okay. Can you see?
Yes, perfect.
Thank you.
Thank you.
So my next lecture will be about calcium carbonate. I'll give just basic information about calcium carbonates because it's, first of all, it's possible to find a lot of information on the web, and you can do it later on in your own way. I will start with this claim: the calcium carbonate is ordinary mineral. I'm sure that most of you are aware that calcium carbonate is one of the most abundant mineral. Here on this map, you can see the distribution of calcium carbonate, global distribution of calcium carbonate. So the fact is that 4% of Earth crust is made of calcium carbonate, 20% are all sedimentary rocks in the form of chalk, limestone, tufa, travertine. Distribution, global distribution is really incredibly so. Last huge amount of United States are covered, Northern America are covered with the similar is in Croatia, Asia, Middle East, Southern Australia. All these regions are covered with limestone. Similar situation is in the sea. So 25% of sea floor sediment contain more than 30% of calcium carbonate. This blue region on this map show that calcium carbonate is dominant in the Atlantic Ocean, Indian Ocean, southern part of Pacific Ocean. You are probably aware of geological appearance of calcium carbonate in the form of karst or limestone, tufa formation, travertine, chalk, even stalactite and stalagmite underground. It is very important biomineral for all invertebrates. Typical precipitation of calcium carbonate. It is used as a protection in shells, in other organisms, but also calcium carbonate in the form of limescale is all around us in the techniques. Here are two examples of unwanted crystallization, precipitation of calcium carbonate. Even if you take a look on the web, you can see a lot of information about calcium carbonate. In Wikipedia, you can find all details about molar mass, size, melting point, boiling points, solubility, and all. But it is indicative, on the other hand, that when talking about, for example, density, you can see only information about calcium and aragonite. It means that something is missing. Most of you know that there are another polymorphs, and similar is solubility product. They gave only one solubility product, but there should be at least three, actually 6 solubility products for calcium carbonate and its formation. There are also illustration of calcite in the form of Iceland spar, aragonite, marble, travertine, and tufa. About polymorphs and forms of calcium carbonate and environmental conditions. Probably most of you know that calcite is a stable modification. Aragonite and water are other polymorphs. You can see some micrographs of waterite, aragonite, and calcite. They're really typical. Also, calcium carbonate, appears in the form of hydrated modification, like calcium carbonate hexahydrate, EKI, and calcium carbonate monohydrate. They are not so widespread around the world, but there are some occasions. For example, EKI can be found in a cold environment, in a seawater that is relatively high, cold. Amorphous calcium carbonate is also actually a hydrated form of calcium carbonate without any crystalline structure. It is known that appear in a natural system. It is stabilized by different organic or cationic modification, and it is typical precursor in a biomineralization. I already said the calcite is most stable polymorph. It is widespread mineral. It covers 8% of Earth crust. Actually, when we talk about calcium carbonates and the appearance on the world, we talk about polymorph calcite. Calcite was formed during different periods of Earth history. It was not just one moment when it appeared. What is also very interesting for calcite is the fact that it can appear in a really large number of forms. At the moment, there are about 80 crystal forms of calcite. That is much more than for other isostructural materials. Calcite appear in a trivial crystal system in which calcium is coordinated with 6 carbonate ions. Here you can see typical morphological, typical formations of calcium carbonate. The typical habits of calcium carbonate, actually the most typical is rhomboidal calcite. It's a stable modification, morphological modification of calcite. Less common is scalenoid. It goes by tone. Less common is scalenoidal calcite, but it can also appear in a form of microcrystalline aggregates. Aragonite is less stable modification, although the stability is very close to stability of calcite. Actually, it's stable at elevated temperature and high pressures, but also in the presence of magnesium ion. Magnesium ion is very important for formation of aragonite, as you will listen later on. Geological formations of aragonite actually slowly transform to calcite, but this process is so slow that it lasts for 10 or 100 million years. It is very important biomineral, particularly in corals, but also in mollusk shell. Laterite aragonite appear in the form of orthorhombic crystals in which the calcium is coordinated with 9 carbonate ions. Typical habits of aragonites are prismatic, acicular, columnar, globular, and so on. Laterite is the least stable polymorph. It is relatively uncommon in nature because it either fastly transforms in aqueous solution or its appearance is only in a biomineralizing systems or pathological mineralization system like gallstone. Hexagonal crystal system of laterite is one in which calcium is coordinated with 8 carbonate ions. Typically, laterite appear in a form of microcrystalline aggregates, but here you can see some crystalline modification of aragonite, which can be found in nature. In a synthetic system in laboratory, it's very difficult to produce monocrystalline laterite. I started to talk about calcium carbonate as an ordinary mineral, but it is not so ordinary. So I'll try to show you something that may be interesting facts about calcium carbonate. So I call it, some condition, it could be extraordinary minerals. So I wonder if you know that the highest man-made structure in a history for a long time was made of calcium carbonate. That was a great pyramid. It was high, about 150 meters, built up in 2,500 years before era, and only in a 12th century there was a higher building made in a history. It was not made of calcium carbonate. This what you can see here is not only calcium carbonate. This is calcium carbonate was cover of this structure actually. It is also good to know that calcium carbonate can be produced only in aqua solution by precipitation reaction of calcium carbonate ions. So calcium carbonate is actually found only on Earth. But the question is, yes, what about other objects, other planets like Mars or Jupiter, Moon, Europa actually. They are covered with water. There was water on Mars, but also on Europe, on Europa. There are a lot of water. Volume of the water on this Moon is probably higher than all water in Earth oceans. So, question is there any calcium carbonate on other objects in a solar system? And this is actually somehow related to search for extraterrestrial life. Namely, there is a class of meteorites called NSC meteorites, which were found on the Earth, and elemental isotopic composition show that they are part of Mars rocks, and there is also found relic of Mars atmosphere. Such meteorites were found on Earth. They were found on the Antarctica as a result of a collision of Mars with some object, and detritus arrived to the Earth. Actually, on one of such meteorite was found calcium carbonate and some structures which resembled organic forms. So it may be the calcium carbonate will be proxy for confirmation of running water on the Mars. I will also tell you something about calcium carbonate and seawater because I think it's relevant for FishMed and your experience, your expertise. So seawater actually consists from water and mineral phase. The question is how water appear on the Earth. The water is probably a result of volcanic activities. It was appeared by degassing from molten salts rock. Another hypothesis assumed that water comes from the comets on the Earth at a very early period of early bombardment of the Earth. On the other hand, the minerals, a majority of the minerals in seawater is a result of weathering and rainfall washout of the ground during the early history of the water. The concentration of sodium additionally increased as a result of leaching from the ocean floor, while these anions, chloride, sulfate, and hydrogen hydrocarbonate result of outgassing during the volcano or from the Earth interior during the volcano activity. The fact is that the salinity of the ocean water, seawater is stable during the history, but the ratio of calcium versus magnesium change. And this is very important and relevant for seawater, and you will see later on the precipitation of calcium carbonate. Calcium carbonate precipitate in seawater. Precipitation of calcium carbonate in seawater can be either inorganic or biological. inorganic precipitation of calcium carbonate was dominant during the early time of history, during the Precambrian, and it is called by microorganism and formation of stromatolites. Modern seawater is still saturated with respect to calcium carbonate, and it can precipitate, calcium carbonate can precipitate in the form of ovoids or pellets. Biological precipitation of calcium carbonate was dominant during the Phanerozoic, this is last 540 million years of the Earth history. The mineralogical composition of biologically precipitated calcium carbonate depends on the organisms. So low magnesium calcite is produced by brachiopods, planktonic foraminifera, and coccolids, while high magnesium calcite is the result of metabolism of benthic foraminifera, echinoderms, coral algae. However, aragonite also precipitate as a result of molds, green algae, sponges, and corals, of course. I said already that during the history, calcium carbonate precipitate. And nowadays, it was either precipitation of calcite or aragonite, or high magnesium calcite. Therefore, during the periods of the Earth history, there are some periods that are called calcitic sea. During this period, low magnesium calcite dominant as an inorganic precipitate. It produced a carbon hard ground in the form of calcitic ovoid, calcite cement. At that sea, at this calcitic sea, aragonite shell that were eventually present were dissolved. On the other hand, the aragonitic sea, this is actually the modern sea, is characterized with high magnesium content in seawater. Now we are in this period, and only aragonite high magnesium calcite can be dominant inorganic calcium carbonate precipitate. The question is, why calcitic sea? Why during the periods calcitic sea was dominant? The explanation is related to chemical processes that happened during this period, namely the rapid sea floor spreading. You can see on this map this mid-ocean ridges is a place where seawater can circulate it and contact the lithosphere. During that process of hydrothermal alteration, concentration of magnesium is reduced because calcium-rich minerals become magnesium-rich basalt or clays. So low magnesium seawater, low because magnesium was reacted and was present in a basalt. Low magnesium content favors the calcite precipitation. Another parameter which causes the formation of calcitic sea is actually the global greenhouse condition. During the certain period, the volcans emitted a high concentration of content, which actually favors the calcite precipitation. I'm sure that you know much about composition of modern seawater, and seawater is characterized mostly by salinity, which is defined as a quantity of dissolved salt in water. On this map, you can see, and we already said that it is more or less constant, but yes, of course, it depends on the position and temperature of the seawater. You can see the salinity is the highest actually in the Mediterranean Sea and the Red Sea, but also high salinities observed in Atlantic, Northern and Southern Atlantic Ocean. pH of water is range is about 7.5 up to 8.4, and it is more or less stable. At 35 salinity, this is average salinity of the seawater, many components can be found. So the major components in a seawater are chloride and sodium, magnesium sulfate, calcium, potassium hydrocarbonate, and also there are also a lot of species that are much lower concentration. It's interesting to know that concentration of calcium and sodium is the highest. After that, the third most abundant salt mineral is magnesium and sulfate, and finally calcite. The concentration of calcium and potassium is actually 5 times lower than concentration of magnesium. And this is very important fact you will learn later on. We already mentioned that seawater is a precipitating system, calcium carbonate precipitating system, because seawater is supersaturated with respect to calcium carbonate. All calcium in seawater is present in a different in the form of different ionic species. So it's not only in the form of calcium 2+, there are also a lot of ion pairs of calcium, but also ion pairs and distribution of carbonate as well as magnesium. The formation of ion pairs is important because it actually lowers the concentration and activity of free calcium ions. Equilibrium in seawater or supersaturation is defined as a product of calcium and carbonate ion divided with the solubility product of calcite or aragonite. And here on this map is shown the distribution of supersaturation, surface supersaturation. Seawater is most supersaturated again in Mediterranean, Arabic Ocean, Arabic Gulf, Red Sea, also Northern Pacific, South Pacific, and majority Atlantic Ocean and the Pacific. The lowest supersaturation is in the region where the high impact of sweet water is running water dissolved. The seawater, it is an Antarctic region, and Arctic region. Already mentioned the role of magnesium on precipitation of calcium carbonate in seawater. Precipitation of calcium and aragonite definitely strongly depend on the ratio magnesium against calcium, but also the temperature is important parameter. So it is known, and it is shown in this diagram you can see here, that at low magnesium and low temperature, low magnesium calcium ratio and low magnesium, calcite is dominant phase. This value of 5 is typical for seawater. So at temperature that are higher than 8 degrees or 10 degrees, aragonite is dominant precipitate of high calcium, high magnesium calcite. At the magnesium calcite region ratio 0, and at very high temperature, like 60 degrees, this is shown here, aragonite is dominant precipitate. The explanation why aragonite dominate when magnesium concentration is high lie in a fact that magnesium ions, which are strongly hydrated, preferentially absorb on calcite. Namely, magnesium carbonate in the form of magnesium is structurally with calcite. So they are constituting or somehow constituting ion on calcite, and by their accumulation on the surface, they inhibit the calcite formation, and in this way promote the aragonite formation. Another explanation is related to likely and easily incorporation of magnesium into calcite crystal lattice. In this way, the solubility of calcite is strongly increased, and such calcite is actually more soluble than aragonite. On this graphical presentation here, you can see how strongly magnesium can be incorporated in a structure of calcite. Even 20% of magnesium can be incorporated, and the solubility product of such material is much lower than solubility product of calcite. On the graph before, on this map, I showed the distribution of supersaturation of calcite on the seawater. Actually, there exists a vertical distribution of calcium carbonate in a water column. In a shallow water, solution is seawater is supersaturated with respect to all polar calcium carbonate. Therefore, the shells of that marine organism are preserved in the shallow water. Actually, in such occasions, in such system, there is no significant spontaneous precipitation of calcium carbonate, although it is relatively highly supersaturated. We notice supersaturation of 5 or even 8. The explanation is related to magnesium concentration that is high, which inhibit the calcite nucleation, but also the aragonite nucleation is suppressed by the presence of organic phosphate in the water. On contrast, from shallow water, deep water are undersaturated with respect to calcium carbonate polymorphs, since the solubility of polymorphs increase with increasing pressure and salinity, but also it decreases with temperature. In this region, calcitic and aragonitic shells are dissolved. The distribution of calcium carbonate sediment is related to the depth, seawater depth. So in the mid-depth zone, this is the zone up to 3.5 kilometer, seawater sediment typically contain 85 to 95% of carbonate. In the transition zone, this is just below 3.5 kilometers, calcium carbonate content dropped to around 10%. In the abyssal depth, there is no calcium carbonate found. Some terms like lysocline are related to distribution of calcium carbonates in the water. The lysocline is a depth in the ocean below which the rate of dissolution is dramatically increased. Calcium composition depth is actually the depth at which calcite deposition is completely compensated with and inhibited with dissolution. Calcium carbonate has an important role in the seawater, and certainly the most important is fact that this is a major buffering mechanism in the seawater. So during the dissolution of calcium carbonate, there is also a shift or equilibrium between bicarbonate and carbonate ions, which can after that buffer any income from carbon dioxide from the water. Calcium carbonate actually regulates the intensity of carbon dioxide exchange at the interface water. And all this story is related somehow to global warming and seawater acidification. I show here a few calculations which show that at a partial pressure of carbon dioxide of 3.3, the pH of the water or seawater is 8.25. Such water is supersaturated with respect to two major polymers. If we increase the partial pressure of carbon dioxide to 6.6, the pH of the water will decrease. It will be more acidified, but still this solution will be, this seawater will be supersaturated with calcite and aragonite. Additional increase up to 1.65 atmosphere increase of partial pressure and distribution in the water column decrease the pH of the solution, which becomes supersaturated only with calcite. So it means that any aragonite that will be appear there will be just made in the phase of saturated solution. It will be in equilibrium. And finally, a few words about calcium carbonate on mainland and about a few words about karst topography. I should emphasize that most calcium carbonate that can be found on the land is actually formed by the diagenesis of seawater sediments. So chalk is a calcium carbonate that was formed before 70 or 120 million years ago, and it is a result of sedimentation of dead organism, of dead planktonic or benthic protista organism like foraminifera. Limestone is, on the other hand, 340 million years old, and it is the result of sedimentation of phytoplankton, coprolithophores. Marble is actually metamorphic limestone on chalk, which come out somehow on the surface. Karst landscape is something convenient and recognizable to most of us. It is the results of weathering of Earth's surface and erosion of dense carbonate rocks like calcite, limestone, or dolomite. Typical landforms you can find there are doline, caves, limestone pavement, also stalagmite or stalagmites. The actual mechanism of limestone dissolution and subsequent precipitation assumes several steps. In the first step, carbon dioxide is present in atmosphere, is somehow absorbed by rain, and such water is acidified and it contains additional concentration of hydrogen ions. The acidification of such water is enhanced in a contact with ground, which is a result of perspiration of roots, but also from the dead organisms. During this process, the partial pressure of carbon dioxide in the water additionally increase, and it's much higher than 10 to minus 3. Such acidified water can dissolve the calcium carbonate, and this is the reason why all these caves, all this form in a karst can appear. However, after leaving such acidified water the underground and entering to the surface, they start to be in contact with the partial pressure of the air, which is low. So the excess during the Henry equilibrium, the excess of carbon dioxide should leave the water, coming out like in the form of springs, and therefore it called the lowering of the pH caused the precipitation of calcium carbonate in the form of some form like stalagmite, stalactite, tufa, or even lake sediment. And this is what I plan to talk about calcium carbonate. If you don't mind, we can have a break now. So we can continue in a 5 or 10 minutes if you don't mind.
That's okay. See you in 5 minutes.
10 minutes, okay.
10 minutes. Okay. Thank you. Okay, Prof, we are here. Thank you. We don't see your presentation.
You don't see? Okay.
You have to reshare.
Is it better now?
Yeah?
Can you see?
Yeah, can we?
Thank you.
Thank you.
So shall I start, or we can wait a bit?
Yes, we can start.
We can start. Okay, thank you. So the following lectures are supposed to be a bit more practical. I will try to show you some model systems that we investigated with emphasizing on biomineralization and on the environment. Actually, I will try to demonstrate how to use crystallization techniques, crystallization knowledge to make some interpretation of precipitation system. I will talk only about calcium carbonate. Precipitation system that may be relevant for biomineralization. So I know that you know a lot about biomineralization. You have good professors to give you the lecture about that. So, but I'll make some small introduction about mineralization, biomineralization. So biomineralization is defined as a study of processes that lead to the formation of structured organic or inorganic materials which are generated by living organism. It is an interdisciplinary study between chemistry, biology, and material science. It is also very relevant for different, for example, paleontology, geology, geochemistry, biomedicine, but also materials. I like to emphasize material science because there is a very good reason. So calcium carbonate biomineralization is related to marine, freshwater, and terrestrial organisms. Calcite is predominantly precipitated by foraminifera, coccolithophores, aragonite, of course, by corals, but mixture of aragonite and calcite appear in bivalve shells, while waterite and amorphous calcium carbonate are a bit more rare, at least by volume, but they are very often form as a precursor phase and also appear waterite, particularly in a fish otoliths. Why I emphasize material science? Because production of materials by simple processes like biomineralization and mild temperature, pressure, and chemical environment is a holy grail for material science. Mollusk shell produce 95 composite with 95 up to 99% of calcium carbonate and just a small amount of organic component. This composite actually improved the fracture toughness that could be even 3 times greater than for the respective analogical inorganic crystal. That is definitely something we can call advanced materials, or particularly if we consider that it was produced at mild temperature, pH that is low, and so on and so on. Organic part contains soluble and insoluble macromolecules that are proteins, sugars, and lipids. And it is supposed that they are responsible for crystal nucleation and growth. Each organic component is typical for specific mineral layer or even for specific biological species. It is possible very often that different mineral layers have a different polymorphic composition, particularly calcite and aragonite, as it is example with these shells you can see here. We are talking about nacre as this mineral phase that is particularly strong in this composite. Aragonite platelets are arranged in a parallel lamina which are continuous at spread during the shell, while the organic component is made of chitin, leucine, or silk-like proteins. And now I will show several examples of model system. I will make very simple explanation for what happened there to show you the methodology, that is emphasize the methodology, and to somehow emphasize that the importance of different parameters that is relatively simple may lead to formation of complex structures. So in this first system, we investigated the influence of initial concentration or supersaturation, the ionic ratio, but also the chemical complexity on precipitation of calcium carbonate. This system is actually defined as a system which mimics the inorganic environment for calcium carbonate biomineralization. Typically, in a biomineralization, the role of small and large organic molecules are considered to be responsible for properties of mineral phase. But we try to show that even the inorganic composition of inorganic ions should be considered in interpretation of the properties of mineral phase. The question with which we put are how to find the answer, how the initial supersaturation can influence the polymorphic composition, but also the morphology of calcium carbonate, how the constituent ion ratio, so calcium carbonate ions, influence the morphology, and also the role, what is the role of ionics and the addition of, let's say, relevant inorganic components. When I said relevant inorganic component, that I mostly think about magnesium ions. So even here you can see 3 precipitation diagrams. I showed in the introductory lectures schematically show the precipitation diagram, which has very straight lines which connect the identical supersaturation. Here we have 3 systems called simple, complex, and so-called physiological system, in which we succeed to produce pure calcite. This is the red one. Blue is laterite and aragonite, just to using different inorganic components. So we'll start with what we call simple calcium carbonate precipitation system. Why we call it simple? We call it simple because we prepare the precipitation system by mixing calcium and carbonate components, which contains only calcium ions. Calcium was introduced in the form of calcium hydroxide, and carbonate ions only in the form of carbonic acid. So after precipitation of calcium carbonate in a solution remain only H plus and OH minus. So there are no co-ions in this system. The precipitation domain which was investigated here was relatively wide. So we started with 10 to minus 4 moles of solution. And we finish with a much higher concentration. So supersaturation range change from 35 up to 0. The temperature of investigation of this system was 25 degrees, and we analyzed the samples after 60 minutes. You can see on this precipitation diagram some dots. You can see full dots and empty dots. Empty dots indicate that, empty dots indicate that there is no precipitate obtained after 60 minutes. Full dots show we have precipitation in this. You can also see these isergons, so identical supersaturation, 5, 10, 20, or 35 are indicated. So it means at this point, let's say in this point, this is supersaturation 5. We have equal concentration of calcium ion and equal concentration of carbonate ion. So actually in this system we obtained two precipitation domains. This one, very broad, is a domain in which we identify calcite. In this domain we identify a mixture of calcite and vaterite. And we already said that we want to investigate how the supersaturation indicate how the supersaturation cause the changes in polymorphism and other properties of the calcium carbonate. So we selected 3 points here. These 3 points lie on this equilibrium equimolar line. So it means that on this line the concentrations of calcium carbonate are identical. So we investigate the system in which calcium and carbonate ions are equal, calcium hydroxide and carbonic acid are introduced in equal solution. We wanted to see what the properties of precipitate will be at supersaturation 5, 10, and 30. And after structural analysis, we find that in this red point, we obtain only calcite. Calcite was also obtained here in this green point. And actually, it was not, this is the so-called calcite domain. In all this region, we have calcite. So it was found here as well. But also, we obtained the calcite appeared at a high supersaturation in a mixture with vaterite. So this is an X-ray diffractogram which showed that beside calcite, we have vaterite. We observed the morphology by using the SEM microscopy. And in this region, at this relatively low supersaturation 5, we obtain polydispersed and very irregular rhombohedron, calcite rhombohedrons. I mentioned before that rhombohedron is a stable calcite morphology. At increased supersaturation in supersaturation 10, we also obtained rhombohedrons, but they were very completely monodispersed. They are about of the same size, and they are regular. And finally, at high supersaturation, we obtain spherulithic particles that are vaterite. We know this is vaterite, and these rhombohedrons are very regular, and they belong to calcite part of the precipitate. So the mechanism assumed the formation of this precipitate said that at low supersaturation domain, we had we have slow heterogeneous nucleation, and therefore irregular particles were obtained. At higher, or we can call it medium range supersaturation, the nucleation was much faster. It was still heterogeneous, and the particles that appear are regular, so it means that nucleation was faster, and the shape of this crystal is also relatively regular. At high supersaturation, we have initial formation of unstable polymorphs. Maybe at time 0, there was also some amorphous phase which appeared, but we didn't detect it because we made the analysis after 1 hour. And this unstable polymorph like vaterite continues to transform to calcite. So besides supersaturation, we also try to analyze how the constituent ion ratio, so ratio between calcium hydroxide and carbonic acid, change the properties of the precipitate. For that person, we selected this middle range of middle supersaturation, medium supersaturation, and we selected supersaturation 10. This is this isogon 10. So in this red point, in this place, we have equimolar ratio. We have calcium against carbonic acid 1:1 concentration. In this point, we have a much higher concentration of calcium hydroxide. Concentration of calcium hydroxide here is 10 to minus 25, while concentration of carbonic acid is less. It's 8 times lower. And finally, in this point here, the concentration of calcium hydroxide is even much higher. It is 10 times higher than the concentration of carbonic acid. In all this region, this region, we know that there should precipitate calcite. We learned that this is calcite, and actually we confirm this by structural analysis, how the X-ray diffraction. But the morphology, which was observed by electron microscopy, show that in equimolar region we have regular calcite rhombohedrons. By increasing the calcium concentration, we observe this shape of crystal. We call it scalenohedral crystals, and you can probably remember they are less stable morphology. But when we additionally increase the concentration maximally, I said maximally, what was allowed with this precipitation system, concentration of calcium hydride. So this is simple system in which concentration of calcium ions is extremely high, and the pH is also relatively high. We obtain spherolithic calcite particles. Explanation of this is related to the fact that at high pH, calcite structure can absorb hydroxyl ion, which in turn block somehow the place, the crystal face from entering from calcium carbon ion, and the morphology is, as you can see, spherolithic calcite was observed. So that was about simple system. Now I will show you how the situation looks like in a system which we call complex precipitation system. Complex is because in this system we apply mixing of calcium chloride and sodium carbonate. This is well soluble salts of carbonic acid, calcium chloride, and one would say that there no influence of co-ions is expected. But during this precipitation, we have formation of calcium carbonate and the sodium chloride ions, besides hydrogen ion, hydroxyl ion were present in the system. The precipitation domain is identical to show before. It is in a range between 35 and 0. Temperature was 25 degrees, and analyzing time was 60 minutes. After 60 minutes, we analyze the content and the morphology of the precipitate. You can see the isogones are banded. That is a result of ion pair formation. They are not so banded as in the case of calcium hydroxide system, and two domains were strictly divided. In this blue domain, we obtain vaterite. exclusively water. In this region, at high supersaturation, we obtained mixture of waterite and calcite. So in this system, we try to analyze what is the role of supersaturation and ion ratio as well. We know that at supersaturation, at lower supersaturation, this red dot, we have a low supersaturation region. It means that heterogeneous nucleation started, and we obtain formation of metastable polymorph. So we obtain lens-like waterite aggregates here in this region. In the region of higher supersaturation, we have medium supersaturation and heterogeneous nucleation as well. We, in this green region shown by green cross, we have higher calcium ratio than in this yellow region, and we obtain here lens-like waterite aggregates as well. However, on this yellow cross, it means this is a simple system in which we have excess of carbonate. Waterite change shape to spherical aggregates. And finally, in the region of the highest supersaturation, we obtain mixture of calcite and waterite, and the calcite waterite that could be found here is much smoother than this calcite. So we can conclude that the high supersaturation domain in which fast homogeneous nucleation started is responsible for formation of unstable polymorph, which subsequently transformed into stable. Even actually, transformation in this region didn't proceed to the end, so we can still find majority of the waterite and only a few calcite. Calcite is stable in this region. And finally, I will demonstrate how the precipitation proceed in a system which we call physiological system. Physiological system is system in which we use calcium chloride and sodium nitrate, sodium carbonate solution, and we also increase the ionic strength. Ionic strength was increased by the addition of sodium chloride at the concentration of 0.15 moles, and also magnesium chloride was introduced into this system. Magnesium, I explained you before, is very important ion when in connection to calcium. So the equilibrium we can hear in this system caused by this precipitation assume mixing of calcium chloride, sodium carbonate, sodium chloride, magnesium chloride, and we have only one precipitate, that is calcium carbonate. But also we have high concentration of sodium chloride or ions, and also hydrogen and hydroxyl ion. The precipitation domain, supersaturation domain, varied in a range from 35 to 0. Samples were analyzed up to 60 minutes, and the temperature was 25 degrees. This color indicates this region. In this region, we obtained aragonite. So, in contrast to previous system, we succeeded to precipitate aragonite. We also can observe, you can see these empty dots here, that we obtain very wide broadening of metastable region. So solution is supersaturated even from this step here, but supersaturation is much strongly suppressed, and there is no precipitation in this region in comparison to previous precipitation system. we investigated and analyzed systems in this region in which the calcium to sodium carbonate ratio was 1:1. But also in each system which we introduced calcium, so in each precipitation system we introduced magnesium. Magnesium was always double in concentration of introduced calcium. So we don't have fixed concentration of magnesium, it was double the concentration of magnesium chloride. We analyzed this equimolar range, equimolar system. So we find that aragonite, which was found here, has a lens-like structure. This is aragonite precipitate at the lowest supersaturation. At the medium supersaturation, aragonite changed the shape. It is a V shapes form. And finally, at the highest supersaturation, we apply here that the supersaturation 35. We also obtain lens-like aragonite structure. So we can conclude that there is no difference on morphology with changing constituent ion ratio, but a different mechanism of aragonite formation at low and high supersaturation has been observed. And finally, we analyze this region, that gray shaded region, in which we obtain metastable formation of metastable polymers that are amorphous calcium carbonate, but also monohydral calcite. With these crosses, we indicate the region where we take the samples. So the red, yellow cross indicate the supersaturation equal to 20. On this place, we identified that precipitate form in a small, smooth, and regular monodispersed spherical agglomerates that show no diffraction peak on X-ray diffractogram, but infrared spectroscopy indicate that we have amorphous calcium carbonate here. So this is amorphous calcium carbonate. Amorphous calcium carbonate was obviously stabilized by the presence of magnesium ion. However, at lower supersaturation, we obtained monohydrocalcite. It was definitely confirmed by structural analysis of X-ray, but also of infrared. This is the shape of these monohydrocalcite crystals. They're actually compact agglomerates of primary small particles. Similarly, at a higher supersaturation, we also obtain monohydrocalcite, but their shape is completely different. They're elongated and actually infolded particles which infold each into another. What we conclude from these experiments is that the stabilization amorphous phase is prolonged. So we have amorphous phase stable even after 1 hour. It is actually surprising. We also observed formation of monohydrocalcite, which was obviously stabilized by magnesium. Actually, in the literature, we didn't find data that the monohydrocalcite can be stabilized by presence of magnesium. Typically, monohydrocalcite is stabilized by low temperature. We don't have more. We didn't have low temperature. We had 25 degrees. And also, it is when we talk about morphology of monohydrocalcite, this modification described in literature is typically precipitate in the form of regular and smooth spherical particles. So that was about the previous model system. We demonstrated that we can produce 3 polymers in a completely unique in a form of only one of these polymers, so calcite, water, and ceramic, just changing the inorganic components which precipitate the system, or by the addition of some common additives like magnesium. In the following system, I will try to demonstrate the influence of inorganic additives like magnesium, but also the anions on the properties of calcium. We apply these additives in a simple system. I should remind you that in a previous experiments in a so-called simple system, we had magnesium that is introduced in the system in which also a high concentration of sodium was present. So in this system, we introduced magnesium in a system which only calcium was present as a cation. Just to remind you about the role of magnesium in a calcium carbonate precipitation. So magnesium is very often found simultaneously with the calcium ions as well in the seawater, but also in an extrapallial fluid. And the fluid, the ratio between magnesium and calcium is 5:1. It is known that magnesium is effective inhibitor of calcium carbonate nucleation growth. It is known that magnesium initiates precipitation of aragonite, and also that it incorporates into calcite crystal lattice forming so-called magnesium calcite, which has actually different properties than ordinary calcite. And also what is very important to mention that mixture salt of magnesium and calcium, that is dolomite, is practically impossible to produce at laboratory conditions. So this is precipitation you saw before. This precipitation system, so-called simple precipitation system, in which we can produce at a condition of no addition of magnesium. We can produce only calcite in this region, or mixture of calcite and waterite in this region. This is, we are talking about equimolar system. Actually, we want to show that in this system of high supersaturation, the kinetics of transformation, the kinetics of crystallization can make the selection of the polymers that we can obtain. Therefore, I didn't mention, but I will show later on that in a previously described system, we have 1 hour of aging of the system. When we follow the kinetics of precipitation in this high supersaturated solution, we obtain this curve. This is a typical curve with those 2 steps. It means that 2 unstable polymers appear here. And indeed, we made the analysis by sampling the precipitation during these 30 minutes, and we found that in this region, at the very beginning, we have only amorphous phase in the system. After a few minutes, this amorphous phase transformed to waterite. So we obtained waterite here, and we obtained calcite, mixture of waterite and calcite in this region. And finally, after 20 minutes, we still have actually mixture of waterite and calcite here, but after 1 hour, we had a complete transformation of this system. The model system we investigated in this case is the one in which we selected this point. We know from previous research that if we mix only calcium hydroxide and carbonic acid, we'll obtain calcite in the form of very regular rhombohedrons. So we decided that it will be a more suitable system to investigate the role of magnesium. We analyze precipitate after 20 minutes, and concentration which correlate to this are 0.005 moles of calcium and 0.01 moles of carbonate. Analysis time was 20 minutes, but the magnesium was introduced into this system by varying their concentration. and varying the source of salt. So it was introduced in the form of magnesium chloride, magnesium sulfate, and magnesium nitrate. The concentration of magnesium changed in a range from 0.002 moles up to 0.01 mole. The results of morphological analysis show the following. So we increase the concentration of magnesium in the form of different salts from 0.5 to 2.0. So in this system, the concentration of magnesium was 2 times higher than concentration of calcium. And it is interesting to know that the addition of different salts produce different calcite. All this you can see here is a calcite. This calcite is relatively regular rhombohedrons at a very low concentration of magnesium. And this calcite is characterized by one of 4 phases. By increasing the concentration of magnesium, 0.011 phases appear on these crystals. So finally we have 104 phase and elongated calcite crystals. What we find here is no aggregate. This is monocrystal of calcite. The situation is a bit different after the nitrate addition. So we obtained rhombohedral calcite, which are elongated, and they obtain dumbbell shape, and actually, except here, we don't observe 1 or 4 phase capping at all. The addition of magnesium sulfide, so besides magnesium, we have the addition of sulfide ions, has a very prominent effect. So even 104 capping was obtained even at very low concentration, but at highest concentration of magnesium, but also sulfide ion, we have aggregates which are elongated along the C-axis. We made a chemical structural analysis and the chemical analysis of the precipitate, and in order to determine the rate of incorporation of magnesium in the calcite, and we found, as you can see on this graph, that the highest concentration of magnesium of more than 8% is found when we apply magnesium hydroxide. Actually, magnesium hydroxide was not applied for the whole range because a high concentration of magnesium hydroxide can cause the formation of co-precipitate that is not wanted. We will not have the only calcium carbonate, we have also a mixture of salt. So by applying the salts, the highest incorporation of magnesium ions was observed for magnesium sulfate system, lower was magnesium nitrate, and the lowest was magnesium chloride. Even in this case, when ratio of magnesium calcite was 2, we obtained 2% of magnesium incorporated, isomorphically substituted in a crystal lattice of calcite. I should emphasize that these observations are consistent with morphological observations, because the strongest effect on morphology was also observed on magnesium salt, and the lowest on magnesium chloride. So in order to additionally influence the influence of sulfate ions on the precipitation of calcium carbonate, particularly calcite, and also specifically on the morphology, we introduce additional sulfite in the form of sodium sulfite. So we find out that sulfite is also incorporated in the structure, and the shape, but also the shape of the calcite change from rhombohedron to spherical calcite, which is obtained only by the addition of sodium sulfate. This structural analysis indicate that sulfate introduced in a percentage of 0.5 when 1 molar calcium sulfate, sodium sulfate was introduced in a solution. We also observed the changes of the structure of the calcite. We measured the change of the crystal lattice, and we found that the crystal lattice of calcite change in both direction of A axis, but also in a C axis. And the change in the direction of C axis is several times higher than in the A axis. So after that, we can make the conclusion about the mode of sulfate substitution into the calcite. Namely, we concluded that sulfate is a structurally substitute to planar carbonate ions, and since sulfate is tetrahedral, it increases dimensions of calcite substructure in this dimension, in a C direction. Before we show that only inorganic ions can change the morphology and also the structure of the calcium carbonate polymorphism. We additionally increase the complexity of our calcium carbonate system by introducing small organic molecules. We selected the amino acids as a good representative due to their role in biomineralization. We investigated these additives in a complex system that was additionally increased by addition of organic matter. The first step in this research was selection of representative amino acids. So we find that it will be interesting to investigate the charge, polarity, but also the chemical structure of side chains of amino acids, and we therefore selected aspartic and tyrosine, which are actually negatively charged at the conditions we apply here at pH 10.7. We also use serine, asparagine, and lysine that has a polar side chain group, and we assume that they can make hydrogen bond contribution to other molecules, but also to the crystal that are in a suspension. And finally, we use alanine and phenylalanine as a non-polar and hydrophobic amino acids. This precipitation experience we perform is what we call previously complex precipitation system. We selected this region of high supersaturation. This is the region where we obtained the mixture of calcite and laterite. That was intentionally because at this specific case, we obtained a mixture of calcite and laterite in a ratio 83% against 17%. And this is important because such design system enable us to make conclusions about nucleation, because calcite and laterite are results of a nucleation process. They nucleated at the very beginning and later on they transform. In this system, we first of all make, of course, the analysis of polymorphic content, and we learn that after the addition of aspartic acid and tyrosine that are negatively charged, we have decrease. So on this graph, there is a concentration of amino acid introduced in the system, and on the ordinate is a ratio of calcite, the content of calcite. So we learned that additional 83% drop after the addition of amino acid to lower value. We obtain even just 25% of water, but very soon the concentration, the content of water or calcite increase. So even at 20 millimoles addition of aspartic acid, we obtain only calcite in the system. Of course, it is the same. Situation is a bit different in the tyrosine addition, because tyrosine give only pure calcite only after the addition of 80 millimoles. In a system with alanine and phenylalanine, that hydrophobic, we obtain practically no change in the concentration. It is very similar, a bit lower, but no change, significant change of the ratio of calcium to water was observed. Polar amino acids show similar trend in a way that initially the concentration, the content of calcite dropped, but after that it increased with increasing amino acid addition. It is most prominent in a lysine system, less prominent in a serine and asparagine, but definitely there is a trend to increase additionally. The morphology of the crystals which we observed in the previous experiments somehow confirm what we concluded, that the strongest effect is formed in a system with the charged amino acid, particularly in the aspartic acid. So in a combination, in a contrast to a reference system in which we have calcite, we follow the morphology of the calcite, which is so pure rhombohedron in a pure system. Even low concentration of aspartic acid cause formation of additional planes, and crystals become spherical, and they are almost perfectly spherical after very high concentration of aspartic acid. So this is a calcite. Similar trend was found in the tyrosine, which show additional planes, formation of additional planes. Here you can still see some vaterite, but at highest concentration there is only calcite with a lot of planes. Probably with the addition of tyrosine, they will become spherical as well. Alanine and phenylalanine didn't show any significant effect. Calcite appeared in the form of regular rhombohedrons, and vaterite was formed in a form of smooth spherulits. The effect of polar amino acids is somewhat similar to charge, which is also consistent with the structural analysis. The increasing number of new planes is obtained after the addition of amino acids, particularly in the serine system, and less in an asparagine system. We made a structural analysis, and also for the system, similar to what we did with the sulfate ions, and we found that addition of aspartic acids. On this graph you can see the concentration of amino acids and the dimensions of lattice A and dimension of lattice B. Dot line is standard calcite. So the addition in the case of, I will focus on this C lattice, C axis, and aspartic acids, the dimension increase with increasing the concentration. Similar trend was observed for tyrosine, which also increased the dimensions in a direction. The effect was not so pronounced in a polar and non-polar bit, let's say more pronounced in the case of polar amino acid, but there is no significant changes in the case of non-polar, completely polar amino acids. We measured the content of incorporation of aspartic acid in a crystal acid, and we find out that increasing concentration of aspartic acid caused the increasing incorporation of aspartic acid in lettuce. We also find out that this observed relative change of crystal lattice in a C direction with increasing aspartic acid addition in the system can be explained with on a similar way. So it indicates that we have incorporation in a aspartic acid in a crystal acid, and substitution of carbonate ions. So a kind of conclusion for this part of experiments is that non-polar amino acids show exert almost insignificant effect on calcium carbonate precipitation by charge, and polar amino acids change the morphology, phase composition, but also the crystal structure. The effect is the strongest for aspartic acid, which significantly changed the calcite morphology and strongly distort the crystal lengths. We observed the anisotropic distortion, so it means that distortion is of the lattice is much stronger in the C direction, which indicate that the carboxyl groups of amino acid substitute carbonate group and coordinate. It has two carbonate group coordinate with calcium ion from the different layer. What is also important for further investigation is the clue that relatively strong effect that was observed for polar amino acid may indicate that the hydrogen bonding could also influence the extent of interactions of the salt molecule with calcite surface during the process of crystal growth. I will show you another model system, which actually showed the role of much complex macromolecules on the calcium carbonate precipitation. In this system, we show the role of soluble organic matrix that was extracted from the corals on calcium carbonate precipitation. These investigations were performed in a relatively complex, very complex precipitation system that was very similar to physiological system, but only very similar. So just to remind you a bit about corals, corals biomineralization produce hard skeleton that are made of aragonite. Corals are marine invertebrates, class of Anthozoa and the phylum Cnidaria. They can form compact colonies of many individual polys. They are reef builders. Colony of corals are genetically identical polymorphs, and individual colonies grow by sexual reproduction. They breed sexually by spawning. Another fact related to coral biomineralization is the formation of aragonite, which can precipitate even at high and low supersaturation condition. Spontaneous precipitation is responsible for nucleation of aragonite in coral, while crystal growth of aragonite is start on preformed aragonite crystals. Precipitation system is relatively complex. It is extrapolar solution which resemble actually the composition of seawater, but fact is that there are also a lot of organic matter introduced in this system. The specific goal of our research is first to extract soluble organic macromolecules from different species. We selected Biomineralization europea, but also the Leptosamia pruvoti. The first one is light sensitive, another one is light insensitive. We plan to apply also kinetic approach to analyze biomineralization of aragonite, so not just to make the precipitation diagram, but also to investigate the kinetics of the process in order to discern the role of physicochemical parameters, that is supersaturation, and biological parameter, that is the role of organic matter. And that spontaneous precipitation experiments will be correlated with nucleation of aragonite at high supersaturation, which actually mimic the precipitation in aragonite which happened during the daytime, and it started at relatively high supersaturation, while the kinetics of aragonite will be investigated in order to see how the crystal growth of aragonite proceed in the conditions of low initial supersaturation. Actually, our working hypothesis was that the growth mechanism and nucleation mechanism is different during the innate and the dye precipitation of aragonite in the crystals. Soluble organic matrix was extracted from Biomineralization europea, as I said. This is solid and stony coral, which could be found only in Mediterranean Sea. It is photophilous, while Leptosamia pruvoti, which is also solitary stony coral, is Xanthella species, which could be found in Western Mediterranean Sea and also in Adriatic Sea. One of the first steps was the selection of our research was selection of model system, and by analyzing the literature, we find out that extrapalia concentration of extrapalia fluid is very similar to concentration, the content of anorganic components in the seawater. So we selected artificial concentration that are typical for artificial seawater and introduced the organic components in our system. As I said before, we applied two model systems. The first model system is of high initial supersaturation. In this model system, we will investigate the nucleation of aragonite. The concentration of system is initiated by mixing of sodium carbonate as a mixture which control the pH of the solution. So we apply buffer of sodium salt carbonate and bicarbonate, but also we use the calcium chloride. Total concentration was 0.01 moles, and magnesium chloride that was 5 times higher, like in extrapalia solution. The ionic strength was adjusted by the addition of sodium chloride, and it was 0.3 moles. So I said initial supersaturation was high, and initial pH was also high. That was actually the way how we increased the supersaturation. In another model system that started precipitation at low supersaturation, we start process at low supersaturation, low pH, that 8 now, and it is really very similar to pH of the seawater or extrapalia solution. The concentration of our organic material was varied in a range of 8 ppm to 0.5 ppm or 1 to 8 ppm. You can notice that these concentrations are very low in comparison to what we apply in the system with amino acids. The temperature of which we apply here was 21 degrees, and we analyze our samples after 30 minutes. And here is the result of our morphological examination in a spontaneous precipitation system, a system in which we compare the nucleation of aragonite with morphology of aragonite find in corals. So you can see this figure showed the cross section of septum of skeletons of Balanophila europaea, Leptosamia privoti. So you can notice here two classes of aragonite crystal. This is completely aragonite, but we can notice here early mini crystals that are smaller, and aggregates of small aragonite crystal. This part of septum is called early mineralization zone, and also a fiber zone here. We resemble these conditions by introducing the different concentration of organic matter, and what we find after the highest concentration, after the highest addition, is that this morphology closely resembles the morphology that could be found with coral mineralization zone. Our spontaneous precipitation experiments were performed in a way that we also followed the kinetics. So we follow what happened after a certain period of time, because we want to see if there is any influence on the kinetics of this process in a context of prolongation of starting of precipitation. And indeed, we find out that, so this is a model system. We can obtain any precipitation after a certain period of time, and precipitation ended at supersaturation that is about 1. It converged to 1, so it means it is approaching the equilibrium. This is precipitation of aragonite. But after addition of increasing concentration of organic matter, we can see that start onset of precipitation is prolonged. So in the model system, we have about I can't see exactly, but a few hundred seconds, while at the highest concentration we have about 11 or 12,000 seconds before lapse before we have any precipitation. After starting, the precipitation was relatively fast. So when we put this data as a function of amino acid of additive concentration of additive, we definitely concluded that there is a linear correlation, and that induction time increased with increasing concentration. What is important to emphasize also is that there was no change of mineralogical composition with addition of additive. So that was the first set of experiments performed at high supersaturation. Seeded experiments with those that go at low supersaturation, and again you can see here that experiments start at a lower supersaturation, but there is not really a big change in the shape of this curve. So this shape of the crystals and also the observed induction time lead to the conclusion that absorption on nuclei, but also on the crystals occur, absorption of organic matter. We didn't observe any change on mineralogical composition, but we also found no change on the growth mechanism. So we analyze in a standard way the kinetics, and we can see this is a second order, this is a parabolic growth rate mechanism. So this is growth on in perfect position on the crystal place that in all cases, we have linear dependence. We also measure some induction time that was not so long as in a system of spontaneous precipitation, and we show that there is no significant difference between two organic materials. The results of morphological investigation of seeded precipitation are shown here. So we have addition of increasing concentration of organic matter from balanophilia and leptosamia. And initially we observe so this system where there is no additive present in the system, we observe regular prismatic aragonite crystals. Even here, we didn't obtain any change of morphology, but we observe increased roughness. And at highest balanophilia concentration, we observe even textual reorganization of particles, which all indicate some interfacial interactions. And conclusion we gained here, we said that under high supersaturation condition, we observe significant incorporation of both macromolecule in a mineral structure. Organic matter incorporated in aragonite, but not in calcite. I didn't show you the other experiments which we performed with calcite. Precipitate aragonite appears in form of aggregates of nanoparticles, which resemble those observed in early mineralization zone. Inhibition of precipitation observed a systematic increase of induction time. It was found for both macromolecules. The growth mechanism obtained by seeding experiments indicate the growth of the spiral step and did not change after the addition of organic matter. Indeed, the presence of high concentration induces a change in the morphology and shape, even of these seed crystals. So as a final conclusion, we can say the inhibition activity of balanophilia is stronger than inhibition activity of leptosamia. And also we can conclude the calcification of coral is controlled by both pure physical-chemical mechanism, but also by biological mechanism. That means by the addition of organic matter. And if you don't mind, we can have a few break for about 5 minutes, so we can continue later on with showing what the precipitation of calcium carbonate can proceed in the main lane. Is it okay?
Yes, it's okay.
Okay. In 5 minutes.
Yes, perfect. Thank you. Yeah, Prof, you can share again.
Can we start? Okay.
Yeah, students are coming. Prof, we cannot see the screen.
Can you see something?
No?
You can't see.
Okay, now yes.
It's okay. Sorry.
Okay, we can start. Thank you.
Okay, thank you. So now I will not spend too much of your time. This is the last model I would like to show you. So this model is related to environmental application of crystallization investigation that actually related to environment and precipitation of calcium carbonate on mainland. So just to remind you, we remain that we saw talk about calcium carbonate, which is actually formed by diagenesis of seawater sediments. We talk about chalk limestone and marble, and also about the mechanism of calcium carbonate formation in the mainland in the karst landscape. I also show you this scheme, and which started with dissolution of carbon dioxide dissolution, afterward dissolution of calcium carbonate in underground, and finally precipitation of calcium carbonate after it come out on the surface. One of the possibility of precipitation of calcium carbonate on the surface is precipitation in the form of tufa. And this is what I'm going to talk to you about now. I'll try to demonstrate it, the case of precipitation of calcium carbonate at the condition which mimic the condition in karst water, in which tufa formation is evident. Actually, the main goal of this part I'm going to show is how to set up a representative model system. So it means system which closely resemble the natural environment. Investigation of tufa in the field is very difficult because there are many parameters, biotic and abiotic, and it's difficult to discern the role of each of them. Therefore, we propose to make a relevant investigation in a laboratory. And for such investigation, you need to have a really representative model system. So that is our aim. And this system is very complex. You will learn later on. And we call it system of artificial karst water. Short introduction. Tufa is a porous limestone which is formed by precipitation in karst water at ambient temperature, which is in contrast to travertine, which precipitate at elevated temperature. Tufa formation can be observed either in fluvial channels or in the lakes. Fluvial tufa precipitation appears in springs, braided channels, cascade, but also on barrages. Model we are going to present later on is correlate to formation on cascades. Lacustrine tufa is formed at lake's periphery and built up phytotherm stromatolites and oncoids. Actually, tufa formation is more and more endangered in the world by human impact, not only by the temperature and acid rains, but also by the introduction of phosphorus and organic matter in such water courses. Both of these additives are known to strongly inhibit the precipitation of calcium carbonate. Already said, the mechanisms tufa formation assume all these steps from dissolution of carbon dioxide, dissolution of calcium carbonate, but after leaf of such water and on the surface, there is a specific sequence of events which probably result in the formation of tufa. First of all, the increase of pH after carbon dioxide removal can be caused either by intensive water splashing at waterfalls, but also by photosynthesis or on periphyton. Therefore, these two processes cause this chemical reaction, well known, calcium plus carbon ion produce tufa. But there is also a very specific sequence of events which show on this sketch here. So, at the first moment, at the first phase, in tufa-forming water, it's obtained the diatoms cover the substrate, and diatoms typically excrete the mucus. In the second step, in this mucus is catch the microcrystalline calcium carbonate, which originate from the detritus from the lake water. And finally, at the final step, the tufa start to grow on these calcium crystals. And this is actually only possibility because the supersaturation in tufa is too low to have a nucleation of the calcium. So it has to go on previously formed crystals. We made our investigations on the area known as the Plitvice Lakes. Plitvice Lakes is a position in Croatia. It is oldest and the largest national park in Croatia, which is situated in mountain region. This is the Karst region. It is on UNESCO World Heritage List since 1979, and the system actually comprises 16 cascading lakes. They are divided in upper and lower lakes. It is not just a matter of their distribution in the place; it's a matter of the substrate where they appear. So upper lakes, 12 of them, comprise the largest lake, are formed of impermeable dolomite rock. On the other side, the lower lakes are formed on the permeable limestone substrate, and they form a deep canyon. It should be mentioned that on the outflow of this system, the Korana River started to go up to the source, to Kupa River. A specific goal of our research was actually to determine the rate of tufa mineralization of Plitvice Lakes. This is something that can be done on the field. But also we tried to describe the mechanism of tufa formation in the context of calcium carbonate growth mechanisms. Specific goals was to discern the role of supersaturation and chemical composition of lake water, role of substrate, temperature, but also role of organic matter. Our research strategy assume first screening experiments and physical chemical characterization of lake water. Actually, the first we try to make a physical chemical characterization of lake water and in situ determination of recent supermineralization. After that, we'll make off-site laboratory experiments and make initial screening experiments with different precipitation system with different concentrations of water. On this slide, you can see the vertical cross-section of Plitvice lakes and the sampling position. We selected several representative sampling positions. The first position is on the source of a river, which gives about 70% of all water to the Plitvice lake system. At this position, actually, no precipitation of too significant hasn't been obtained before. The second position is on the outflow of the one lake, big one, and on this position, the first tufa has been appearing in the whole system of the lakes. The second position was selected on the outflow on the largest lake, and the last one is on the outflow of the whole system of the lakes to Korana River. Physical-chemical characterization of lake water was made after analysis of the samples which we take during the season. We make sampling during 3 years, and this is example. This is a kind of table on which we have a different time, different periods of sampling, and what we measure was content of total calcium, magnesium, sodium, chloride, sulfate, nitrate. We also measured the pH on the position. We measured the temperature. We also measured the alkalinity, total carbonate content on the field, and we, on the basis of this analysis, we calculated the supersaturation on this position. It is evident from these graphs you can see here that there is a very good seasonal distribution. It is possible to see that there is a seasonal distribution of key parameters. The best example is on the temperature. It could be seen that the temperature is the highest. So these 5 curves is actually 4 or 5 curves are positions on the lake. So we can see that in all lakes the temperature is the highest during the warm season, during the summer or in the early autumn. Similar and the lowest is during the winter period and the cold period. Similar trend, not similar, there is a trend, but this is example of calcium. The supersaturated calcium, maximum calcium concentration was actually observed during the coldest period. Similar observation was found for the supersaturation, and pH had actually the reverse trend. It's also worthwhile to know that the concentration of magnesium actually don't say during the season too much. There is no big changes. That is important for what we are going to do this in a further work. And also it's important to see that dissolved organic matter is also more or less constant during the season, but also there is no big difference between the concentration of organic matter in the different lakes. Spatial distribution of key parameters show that there is a difference between cold and warm season. So red one is warm season. It's possible to see that this first point correlates to the first point, that is a point where no precipitation too far has been obtained. So supersaturation actually increased along the system, and it's higher, and the outflow from the system. pH also increased, and it's the lowest. So this is the pH at the source, and this water is relatively acid, so not majority of the carbon dioxide was still expelled. and it's the highest the outflow to coronary. Calcium concentration decrease is consequence of tufa precipitation, which started here and continue to the end of this place. Concentration of magnesium is more or less constant. It is constant practically. Similar to calcium is a decrease of total carbonate. So carbon dioxide is expelled from the system, from the water column, and also the part of calcium carbonate is fixed to calcium carbonate. Temperature, change of temperature during the warm period, it increased from the source to the outflow. Opposite trend is obtained during the cold period. So besides measuring the critical parameter and sampling the water, we also made experiments in which we determined the mineralization rate. Mineralization rate can be made only in situ on the place. And for that purpose, we use different substrate. Finally, we decide and we find out that the best selection is microscope glass slide that was placed on the holder. Several of these slides were placed here, so we can select, but from time to time take the samples. Sampling of the tufa was made during in a period from February 21 up to October 22. So we have 2 cold seasons and 2 warm period. And this is on this graph is shown how the mass of tufa on these slides increased during the periods, and it could be seen that after some initial period of colonization of the slides, it started to increase, then stop, and it is continue after a certain period. On this differential presentation, it could be seen that maximal mineralization is observed during the August, September in year 2021 and in year 22. We characterize these slides, and after 12 months, we find that calcite, which was found there, is very similar on all of these locations. So this is location Matica, Prošće, Kozjan, and Novaković. Even it's also interesting to see that we obtain even some mineralization on the Matica river, that is most acidic part of the whole system of the lakes. But we obtained some crystallization. It is not significant, but it was so. This is calcite. What we can see here is calcite as confirmed by X-ray diffraction. We also made the characterization after 2 months. This is the period during which the colonization of diatoms can be observed, and we observed, as you can see, different diatoms on different plates. We made chemical characterization of the tufa by using SEM and EDS spectroscopy. And here is the example. This is a cross section of a plate. So this is tufa, this is glass, this is tufa. So it can be seen that tufa, about 2 millimeters of the tufa can be found at a certain period. This EDS spectrum show that there are 2 chemical species here that can be determined. This is a calcium. This is a yellow one, which belongs to calcium carbonate, and silica SiO2 is a blue one, which belong to diatoms. Similar on another location, diatoms are purple, and green is calcium that originates from calcium carbonate. So we conclude that tufa is actually a mixture of calcium carbonate and living organism diatoms and silica. We made a structural characterization by using X-ray diffraction and infrared spectroscopy, and we found that after a prolonged period of time, we have tufa on different location. So at the location Kralj and Novakovic Brod, we obtained tufa which contain 95% of calcite, 4% of dolomite, and 1% of silicium dioxide that originate definitely from diatoms, but also it's possible to have some detritus that contains silicium dioxide. Similar result was found on Novakovic Brod, but interesting on the Kozjak, this is the largest river, we have calcite, but also magnesium calcite identified as a phase. But also we identified much higher concentration of dolomite in this system. After that, we decided to perform laboratory experiments, and just to demonstrate that first step was the selection of precipitation model system. We should decide which concentration to use, which model system, which lake system to use. So our idea was to use the system in which we have high mineralization rate, high supersaturation, and high pH. The inorganic component that should be mentioned, that should be used there, should be carbon dioxide, calcium, magnesium, sodium, potassium, sulfate, chloride, and nitrate. And actually, the initial concentration which we selected as the representative was the concentration at the place where the system is the most supersaturated and position at which we have outsourced to the Corona River. And actually at this place, we made some average and we find the concentration during the summer period change in a certain range, and we made an approximation. Also, what is important for performing these experiments is to have a protocol for precipitation of such artificial karst water should be simple, and it should be suitable to perform the kinetic experiments. So I talk about concentration, and to demonstrate you that we use sodium, calcium, magnesium, and so on, all the other system here, and this is the concentration which we measure on this location, and this is artificial seawater which we apply in our experiments. So it can be seen the sodium concentration is identical, calcium, magnesium, potassium, chloride, nitrate, a bit highest concentration was in a natural water in the Novakovic Brod than in artificial seawater. The bicarbonate concentration is similar, it couldn't be identical, and actually this is something what changed from time to time. The pH of our experiments was also similar. It's a bit higher in our system because we have to initiate the precipitation by increasing the pH. So the results of our spontaneous precipitation in artificial karst water, which resemble the concentration in Novakovic Brod, is shown here on these SEM pictures. We found that there is a difference at different temperature. So at 10 degrees, we found that we have a mixture of calcite, aragonite, and vaterite. Calcite is rhombohedral crystal, not really visible here, but spherical crystals are vaterite. At 20 degrees, we have some calcite, much more aragonite, and some vaterite, while at 25 degrees, we have a lot of aragonite. This is also shown here, and just a bit of calcite. this concentration on 25 degree definitely did resemble what we found on the field. On the field, as you can see here, we find mostly exclusively calcite and some dolomite in this precipitate. So the conclusion could be that this is not a suitable model system. But then we understand that chemical composition of karst water is not only described by inorganic component, there are also certain content of organic matter. The organic matter was expressed in a way that we don't actually know what is the composition of organic matter, although we have a clue what it could be. We determined the organic matter by DOC analysis, and we have to decide what to use here as a model organic molecules. So we decided to use humic compounds. Humic is actually organic compound that is formed by the composition of biomass. This is a major component of dissolved organic matter in lakes and rivers, but it actually consists of two components. One of them is humic acid, and another is fulvic acid. Humic acid is less soluble actually, and it is practically insoluble at low pH, while fulvic acid is completely soluble in water at all conditions. You can notice here that fulvic acid is characterized by a lot of carboxylic group, which actually improve its dissolution in a water. So when we introduce fulvic acid or humic acid in our model system, then we definitely observe some changes. For comparison, this is a model system, and after addition 0.5 millimoles, there are some changes that are observed. So actually, we made a chemical characterization, not only at 0.5 millimoles, but we also increased the concentration of additives, and we can see here how the content of calcium carbonate precipitate change after the addition of fulvic and humic acid at different temperature. On this graph is shown the content of polymorph or certain polymorph as a function of concentration of fulvic acid addition expressed in the ppms. So it could be seen that after the addition of fulvic acid at 2 ppm concentration, calcite is dominant polymorph in all systems, even at 10, 20, and 25 degrees. Situation is not identical in a humic acid system because at highest temperature, at 2 ppms, the dominant polymorph is aragonite, which is definitely the consequence of what we learned before, that increasing temperature, not only the magnesium, can enhance the formation of aragonite. So our model system definitely was selected on the basis of all these experiments, and we decided to use 2 ppm of fulvic acid. Here you can see the morphology of precipitate obtained at 2 ppm addition. If we focus on fulvic acid, we can see that only calcite can be found here, and that at highest temperature, that's about 20 or 25 degrees, the morphology of this precipitate is very similar to what we observed on this position on the Novakovic broth. So precipitation system, this is a kind of conclusion artificial karst water is made by dissolving calcium chloride, sodium carbonate, sodium chloride, potassium chloride, magnesium chloride, sodium sulfate, and sodium nitrate, and concentration of dissolved organic matter is somewhere between 2 and 5 ppms. Supersaturation that is possible to investigate in this system is range between 12 and 3.7, and the range of additives is much higher. In such system, it's possible to investigate the addition of additives which can change the properties of tufa, which may inhibit this process or somehow accelerate. So, final conclusions about this set of experiments: that the investigation of tufa at location on watercourses is difficult. Also, the concentration of major inorganic components and other physical chemical properties varied along the watercourse, not only during the season. The recent tufa, which is obtained after 3 seasons of continuous mineralization on the glass slide, is predominantly calcite and magnesium calcite, while diatoms could also be found. The laboratory model assumes reproducible preparation of artificial karst water, which closely mimic the chemical composition of natural water. So it assumes inorganic and organic components of such water. Actually, mixture of 3 polymers precipitate when only inorganic components are present, while magnesium calcite is the only component when at least 2 ppm of fulvic acid is introduced in the model organic molecules. And this is going to be my final conclusion, and this is going to be end of my lecture. This is literature that is recommended for you, and I will inform you later on. I think within a few days I will be in contact with you, so I will send you this lecture and a list of the literature that is recommended for exam, which we can agree later on about. Thank you very much.
Thank you, Professor.
Yeah. Thanks for your participation in this teaching week.
Okay.
See you.
Okay, see you.
Bye-bye.
We'll be in contact. Ciao.
Ciao, ciao Telja.
Thank you.
Hello, Francesco.